NASA is preparing to turn the sun into a super telescope by using the sun itself as a lens. This concept could allow us to capture high-resolution images of Proxima Centauri b. In theory, we might even be able to see its rivers, continents, and perhaps the lights of cities. If the mission succeeds, it could become one of the greatest scientific achievements in human history. Perhaps, within our lifetime, humanity's first glimpse of an alien city will come not from a science fiction movie, but from a real astronomical image. Humanity has discovered more than 6,000 exoplanets. An exoplanet is simply a planet outside our solar system. But here's the problem. Even the best images we have taken of these thousands of planets show little more than blurry dots. I do not know how you feel when you look at images like that, but I want to see more than a point of light. I want to see rivers, mountains, and continents. I even want to see the lights of alien cities. But there is a very practical obstacle standing in the way. Our current telescopes are nowhere near powerful enough. This is the James Webb Space Telescope. It is one of the most powerful telescopes humanity has ever launched into space, and its primary mirror measures 6.5 meters across. But to take a genuinely high-resolution image of an exoplanet, we might need a mirror 90 kilometers in diameter. An engineering project on that scale is far beyond our current technological capabilities. Scientists have actually been studying a possible solution for nearly a century. The idea can even be traced back to Einstein. In 1992, astronomers discovered the first exoplanet. Since then, exoplanet research has entered a period of explosive growth. At first, scientists relied mainly on two methods to find them. The first involves watching a star for tiny wobbles. Although a planet is much smaller than its star, its gravity still tugs on the star and causes it to move slightly. The second involves looking for a small, sudden dip in a star's brightness. When a planet passes in front of its star, it blocks a tiny fraction of the starlight, much like the moon blocking the sun during a solar eclipse. But both methods are fundamentally indirect. We are not seeing the planets themselves. We are seeing the effects they have on their stars. Naturally, scientists want to do something else. Point a telescope directly at these planets and photograph them. By the beginning of the 21st century, humanity had started to make some progress. But the exoplanets we managed to photograph were still little more than tiny dots. And most of them were not Earth-like planets, but enormous gas giants similar to Jupiter. Even with the Hubble Space Telescope or the largest ground-based observatories, directly imaging a true Earth 2.0 is nearly impossible. Such a planet would simply be too small and too faint. It is theoretically possible, but we would need a telescope 2,300 times larger than any telescope humanity has ever built. And even if we somehow built a telescope that large, we would still face an even more difficult problem. The planet's host star would be overwhelmingly bright. Earth-like planet is roughly 10 billion times dimmer than the star it orbits. It would be like standing hundreds of kilometers away and trying to photograph a firefly flying next to a stadium floodlight. The firefly is already faint, and with an enormous light blazing beside it, distinguishing it would be almost impossible. We do have an instrument called a coronagraph, which blocks out a star's intense light and makes nearby planets visible. But today's coronagraphs can suppress stellar glare by only about a factor of 1 million. What we actually need is a factor of 10 billion. In other words, we are still short by a factor of 10,000. This is known as the contrast problem. But what if we took a completely different approach? In 1915, Einstein published his famous theory of general relativity. Under this theory, gravity is no longer understood as a simple pulling force, but as the curvature of spacetime itself. A massive object like the sun bends the spacetime around it. Because light travels through this curved spacetime, its path is bent as well. About 20 years after Einstein published general relativity, a Czech immigrant named Rudy Mandl was working as a dishwasher in Washington, D.C. He realized that gravity might act like a lens and magnify the light of distant stars. So he traveled to Princeton to meet Einstein and told him about the idea. Einstein was not optimistic at first. He believed the effect could never actually be observed. But Mandl persisted and contacted Einstein repeatedly. Several months later, Einstein finally, and somewhat reluctantly, published a short paper describing the concept. When he agreed to send the paper to a journal editor, he wrote in a letter, "Thank you for your cooperation in publishing this little paper. Mr. Mandl squeezed it out of me. It is of little value, but it will make the poor man happy." He even concluded the paper by writing, "Of course, there is no hope of observing this phenomenon directly." But this time, Einstein was wrong. Decades later, astronomers began seeing gravitational lensing throughout the universe. Light from distant galaxies can be bent, distorted, and magnified by massive objects lying between those galaxies and Earth. This creates beautiful rings of light in space, now known as Einstein rings. Then, in 1979, a scientist named von Eschelmann asked a question that changed everything. Gravity can bend and magnify light. Could we use the sun's gravity to turn the sun into a gigantic telescope? It was a beautiful idea, but the technology it required sounded almost like science fiction at the time. Today, however, it may no longer be merely science fiction. Here is how it would work. Light from a distant exoplanet travels across the universe. As it passes near the sun, the sun's gravity bends it slightly. Because the sun is approximately spherical, light passing around opposite sides of the sun is bent toward the same region. Eventually, those rays of light converge again behind the sun, forming a focal line. This focal line begins at a distance of approximately 550 astronomical units. 1 astronomical unit is the average distance between Earth and the sun, or 149,597,870.7 kilometers. The focal line does not end at a single point. It continues outward and, in theory, extends to infinity. Once you travel beyond roughly 550 astronomical units, the sun would appear as a brilliant sphere of light surrounded by a ring created through gravitational lensing. The image of the exoplanet we want to photograph would be encoded within that ring. The sun would act like a gigantic cosmic funnel, collecting photons scattered in every direction from the planet and focusing them onto locations along the focal line at visible wavelengths. This focusing effect could amplify the planet's brightness by a factor of 100 billion. That would be equivalent to having a telescope with a mirror 90 kilometers in diameter. So the basic mission concept is this. First, select the planet you want to photograph. Then identify a line extending directly behind the sun in the direction opposite that planet. Next, send a telescope to a point along that line. Finally, point it toward the Einstein ring surrounding the sun and begin taking pictures. Remember the contrast problem mentioned earlier. The host star is so bright that it is extremely difficult to block out. But the solar gravitational lens approach largely sidesteps this problem because we are not looking directly at the star next to the planet. Instead, we use the sun to focus the light coming from the planet itself. Of course, we still need to block the light from our own sun, but that is comparatively much easier. Existing coronagraphs are already powerful enough to do the job. More importantly, the focal line extends outward indefinitely, so the telescope does not need to slow down and stop at any particular point. It can keep flying along the focal line, continuously taking images as it goes. In fact, the farther it travels, the cleaner the images become, because contamination from the solar atmosphere grows progressively weaker. This is the Solar Gravitational Lens Telescope, or SGLT. So we send the telescope to that focal line. But an immediate question arises. How do we get a telescope that far away? At 550 astronomical units, the destination is already far beyond anything humanity has ever launched from Earth. The minimum focal distance of the solar gravitational lens is approximately 547.6 astronomical units, or 82.3 billion kilometers. Even light itself takes more than 3 days to cross that distance. By the time it gets there, the telescope will be in the space between the stars, immersed in the interstellar medium. Voyager 1 was launched in 1977 and has now traveled more than 169 astronomical units from the Sun. It is currently the most distant human-made object from Earth, but reaching the solar gravitational lens's focal line would require traveling 3.3 times farther than Voyager 1 has, and we cannot simply sit around and wait 150 years. Chemical propulsion, the kind used by every rocket launch you have ever seen, has a practical speed limit of about 5 astronomical units per year. At that speed, reaching the focal line would take roughly 110 years. That is far too long for a scientific mission. Ideally, the people who contribute to a major scientific project should live to see its results. A mission lasting 150 years is unlikely to inspire much enthusiasm. What scientists really want is a mission that can be completed within the span of a researcher's career, or at least within a human lifetime. The goal, therefore, is to have the SGLT become fully operational within 25 years. To do that, we have to travel faster. After years of testing different concepts and weighing the available options, the research team ultimately focused on one approach: solar sails. Photons of sunlight have no mass, but they do carry momentum. This means that when photons strike a highly reflective surface, they exert a tiny push. It is much like crossing an ocean with sails and wind, except this time we would be crossing the cosmos using light instead of wind. To reach a speed of 25 astronomical units per year, the spacecraft would have to perform what is known as a solar dive maneuver. Put simply, the spacecraft would first be placed on a trajectory plunging toward the sun. The entire spacecraft would weigh less than 100 kilograms. As it approached the sun, it would deploy its solar sail. In the proposed design, a central boom extends from both sides of the spacecraft, supporting 16 rectangular sail panels. Each panel has an area of 1,000 square meters. Altogether, the sails would cover an area equivalent to roughly 2.5 soccer fields. The sail is designed this way because each panel can be angled independently, allowing the spacecraft to be controlled with much greater precision. The material would have to be almost unimaginably thin, about 70 times thinner than a human hair. Yet despite its enormous area, the entire solar sail would weigh only 32 kilograms because it would be made from an ultralight, tin-coated carbon nanotube film. The problem is that the sails would pass extremely close to the sun, so they would need to withstand temperatures of 3,200 degrees Celsius, roughly twice the melting point of steel. As the spacecraft approached the sun, the sail panels would first be angled to prevent solar radiation pressure from pushing the spacecraft off course too early. Then, at closest approach, when the spacecraft was just 15 million kilometers above the sun's surface, about 1/10 the distance between Earth and the sun, its proximity to the sun would provide an enormous gravitational boost. The sun's gravity would whip the spacecraft around and fling it out of the solar system, placing it on a trajectory toward the focal line. At that critical moment, the sails would rapidly rotate into position, and sunlight would begin accelerating the spacecraft with tremendous force. This solar dive maneuver could accelerate the spacecraft to 125 kilometers per second, or roughly 26 astronomical units per year. At that speed, it would take only 20 years to reach the focal line. After 2 years of flight, the solar sail would have largely outlived its usefulness because sunlight in the outer solar system would be too weak to provide meaningful thrust. The sail would then be discarded and left to drift into space. After 7 years, the spacecraft would overtake Voyager 1. Finally, after a full 20 years, the telescope would reach the focal line and begin a 10-year observing mission. Now imagine that we build the telescope, launch it, wait 20 years, finally switch it on, only to discover that it does not work. What, then? The SGLT team has considered this possibility, which is why the plan is not to launch a single spacecraft, but hundreds of them. Each launch would carry 6 CubeSats, each assigned a specific role. Some would carry components of the telescope's mirror system. One would carry a coronagraph to block the sun, another would handle communications with Earth, and one would carry a nuclear power source, because sunlight at their destination would be too weak for solar panels to operate effectively. Each small CubeSat would carry its own solar sail, allowing it to place itself on the correct trajectory. Once released, the CubeSats would autonomously assemble themselves into a mission-capable spacecraft. The telescope itself would not need to be very large. It would require only a mirror approximately 1 meter across. The sun has already done the hardest part of the work. All that remains is to collect the image from the correct location. And the team would not launch just one of these systems. Producing an actual image of a planet would require 5 or 6 complete mission spacecraft because reconstructing an image of a planet from its Einstein ring is an extraordinarily complex task. More boldly still, the team wants to launch a complete group of spacecraft every year. The researchers call this architecture a string of pearls. It would resemble a necklace stretching from the sun into interstellar space, with each pearl consisting of a group of small spacecraft. The groups would be launched 1 year apart, so neighboring pearls would be separated by approximately 25 astronomical units, roughly the distance from the sun to Neptune. This is a remarkably resilient design. One pearl encounters a problem, or one of its telescopes fails. The overall mission can continue. The pearls would use laser communications to relay data from one group to the next, passing it all the way back to Earth like a relay race. The complete image would contain only about 6 megabytes of data and would take approximately 13 hours to transmit. Of course, that does not include the time required for the signal itself to travel back to Earth. Each pearl would carry all the hardware needed to form a complete imaging system, including telescopes, power sources, and communications equipment. Together, the pearls would serve as a communications relay chain, an observing fleet, and a comprehensive system of backups. Pearls launched later could also incorporate newer and better technology. The group launched in the 5th year, for example, could take advantage of 5 additional years of progress in materials science, computing, and artificial intelligence. There is another crucial point. There is not just one focal line. There are infinitely many. Every planet has its own focal line located on the opposite side of the sun, directly away from that planet. This means that we would not be limited to observing a single planet. We could select multiple targets, each with its own focal line. The research team has already compiled a list of candidates. These include Kepler-186f, the first Earth-sized planet discovered in a star's habitable zone, and LHS 1140b, a world sometimes described as an eyeball planet. But the 3 most important targets are as follows. In 3rd place is GJ273b, a super-Earth located 12.4 light-years away. Orbits a very quiet red dwarf and receives only 6% more light from its star than Earth receives from the Sun. Among all known exoplanets, it is considered one of the most promising candidates for potentially habitable conditions. In 2nd place is the famous TRAPPIST-1 system, located 40.7 light-years away. contains 3 rocky planets, either within or very close to the habitable zone. This would give scientists an exceptional opportunity to image multiple planets within the same star system. In first place is Proxima Centauri b, our nearest neighbor at a distance of just 4.24 light-years from Earth. It is the closest potentially habitable exoplanet currently known. That also means it would offer the highest achievable surface resolution. If an extraterrestrial civilization truly exists there, the SGLT might be able to detect the traces it has left behind. With these targets selected, the overall structure of the mission becomes clear. Multiple focal lines extend into interstellar space, each with its own array of spacecraft, tasked with imaging an Einstein ring and transmitting the data back to Earth. That is the mission's basic architecture. But when the telescopes finally arrive and begin flying along the focal line, how exactly do we reconstruct an image of a planet from its Einstein ring? This is where the mission becomes truly ingenious. It sounds like science fiction, but it is based on real physics. Consider the focal line corresponding to Proxima Centauri b. Each observing unit would contain 5 telescopes with 1-meter apertures, and each telescope would perform a specific function. Their task would be to take the light from a planet that has been distorted into an Einstein ring and reconstruct it as a clear image of the planet's surface. The image of the entire planet is not simply hidden inside a single ring. Instead, it is projected across the sky into an enormous cylindrical region. The telescopes must therefore move through this cylinder, photographing the Einstein ring from different positions. For Proxima Centauri b, when the telescopes are 650 astronomical units from the Sun, this imaging cylinder would be approximately 32 kilometers in diameter. As the telescopes traveled farther away, the cylinder would expand proportionally. By the time they reached 1,200 astronomical units, it would have grown to approximately 57 kilometers in diameter. Every telescope would carry its own coronagraph to block the brilliant light of the Sun. The problem is that the Sun's active corona would still generate a great deal of noise. Telescope manuals generally tell you never to point a telescope at the Sun. In this case, however, that is exactly what we would have to do. To solve this problem, 4 of the 5 telescopes would image the Einstein ring, while the 5th would remain outside the imaging cylinder and observe only the solar corona. This reference telescope would independently measure the light from the Sun's atmosphere without capturing the Einstein ring. Scientists could then subtract that coronal signal from the images taken by the other 4 telescopes, producing a much cleaner image of the ring. Next, the imaging cylinder would be divided into a grid. Each small square in that grid would correspond to 1 pixel in the final image of the planet. For Proxima Centauri b, when observed from a distance of 650 astronomical units, the spacing between pixels in physical space would be only 31 meters. The 4 imaging telescopes would move through the grid in carefully coordinated patterns, almost like dancers, photographing the Einstein ring at every position. But to obtain an image of the ring that is clean enough to reconstruct the planet, the telescope's positions would have to be extraordinarily precise. An error of even 1 meter at the moment of observation could make the result unusable. After reaching each designated position, a telescope would remain there for 30 to 60 seconds while imaging the Einstein ring. The coronal signal measured by the reference telescope would then be subtracted, leaving a clean image of the ring. At that point, most of the remaining light would be coming from the planet itself. In other words, you would have just captured 1 pixel. The telescopes would then move on, gradually scanning the entire grid. As they traveled farther from the cylinder's center, the shape of the ring would begin to change. This is because the Sun is not a perfect sphere. It is slightly flattened at the poles. As the observing position changes, one side of the ring becomes brighter. That brighter side contains a tremendous amount of information about the planet's surface, although the information remains encoded within the ring. The farther from the center the telescope moves, the more clearly the ring separates until it eventually resolves into 2 bright arcs. Ultimately, the mission would produce an enormous grid of observations, with a gravitationally lensed image recorded at every point. So where is the planet in all of this? This is where the real magic happens. General relativity provides a tool known as the point spread function. It tells us precisely how the image of a planet is distorted into the observed ring. By calculating that process in reverse, we can trace most of the photons in the Einstein ring back to the locations on the planet's surface from which they originally came. We would not use just one grid. These telescopes would operate continuously for many years, and the farther they travel from the Sun, the cleaner the images would become. Eventually, we could combine millions of images of the Einstein ring to reconstruct the final picture of the planet. By repeatedly imaging the same planet over several months, we could also gradually filter out the noise caused by clouds. After all, if you spent 20 years and tens of billions of dollars on this mission, only to end up with a photograph obscured by clouds, that would be a terrible shame. But long-term imaging offers another advantage. It would allow us to observe the planet rotating. As the planet turns within our gravitational lens, we could gradually map its surface from every angle. If we were observing a star system like TRAPPIST-1 with several planets of interest, we would simply identify the imaging cylinder corresponding to each planet and scan them one by one. After decades spent sending the telescopes to the right locations, followed by months of collecting images, analyzing data, and mapping the planet's surfaces, we would finally obtain one of the most extraordinary images humanity has ever produced, a high-resolution picture of an alien world. Take Proxima Centauri b, 4.2 light-years from Earth, as an example. In the final image, each pixel would represent roughly 1 kilometer of the planet's surface. We could see intricate details across vast continents, oceans, and even large lakes, polar ice caps and glaciers, deserts, jungles, forests, and grasslands. We might also see enormous mountain ranges. We could even observe hurricanes forming within its weather systems. Most exciting of all, if an extraterrestrial civilization really existed on that planet, we might be able to see its cities. That would be remarkably direct evidence that we are not alone. Think back to when you were a child, looking up at a star-filled sky at night. Many people have asked the same question. Could someone near one of those stars also be looking up at their own sky? This mission might, for the first time, turn that question from an act of imagination into something we can actually answer. And remember, because we would launch groups of spacecraft along multiple focal lines, we would not obtain an image of just one planet. Every additional focal line would allow the mission to study at least one entirely new world. If we chose a star system like TRAPPIST-1, a single focal line might actually give us the opportunity to study 3 different planets. Nor would we be taking nothing more than beautiful pictures. The data would also allow us to measure the composition of their atmospheres and search for signs of extraterrestrial life. More importantly, we might even be able to determine where particular gases originated on a planet. Suppose, for example, that a planet contained large quantities of methane, a gas that on Earth is often associated with biological activity. We might be able to pinpoint whether that methane came from a particular continent or forest. With observations collected over many years, we could also track the planet's weather patterns and determine whether it was geologically active or whether it had plate tectonics and volcanoes like Earth. If we truly accomplish this and use the Sun to image an exoplanet in another star system, I believe it would rank among the greatest achievements in human history. Might surpass the moon landing, the splitting of the atomic nucleus, and even the sequencing of the human genome. So where does the project stand today? NASA runs a program called the NASA Innovative Advanced Concepts Program, or NIAC, which funds high-risk, high-reward ideas at the frontiers of science and engineering. Slava's team completed its Phase 1 study in 2017, demonstrating that, in theory, a 1-meter telescope located more than 550 astronomical units from the Sun could image an exoplanet. In other words, the laws of physics allow it. In 2018, the team completed its Phase 2 study with $500,000 in funding and achieved 3 breakthroughs. First, it worked out how to reconstruct an image from the Einstein ring. Second, it developed the spacecraft cluster architecture described earlier. Third, it found a way to use solar sails to reach the destination within a sufficiently short period of time. In 2020, the team received Phase 3 funding, the final stage the project has reached so far. To date, only a small number of concepts have ever advanced to this stage. With $2 million in funding, the team developed a complete mission architecture. In other words, it ran the numerical simulations, worked through the engineering design, and reached a clear conclusion. Given sufficient resources, the team could bring this image back to humanity. Slava later received private funding from an undisclosed philanthropic foundation to build a demonstration spacecraft called the Sundiver. Its mission is to test the solar sail technology. According to the team's current goal, the demonstrator will be launched within the next few years. A rough estimate puts the total cost of the full SGLT mission at around $40 billion over 40 years, or approximately $1 billion per year. That may sound like an enormous sum, but compared with humanity's other major engineering projects, it is not inconceivable. It would amount to roughly 1/5 of the cost of the International Space Station and about 1/20 of the cost of the Apollo program. A mission on this scale would also be unlikely to be undertaken by NASA alone. It would more likely become a global collaboration involving many countries, with humanity working together to accomplish something Einstein once believed could never be observed directly. This is real physics, and it is being studied seriously. But the story does not end there, because this idea is about far more than taking a single photograph. Imagine that we really succeeded. We captured a high-resolution image of an exoplanet, and it showed compelling signs of intelligent life. What would happen next? The most remarkable aspect of this idea is that it works in both directions. We could use a gravitational lens not only to receive light but also to transmit signals. In other words, this technology might allow us to build something even more astonishing, a galactic internet. Every star in the Milky Way could serve as a gravitational lens in the same way. For lower mass stars, the focal region would begin closer to the star. For higher mass stars, it would begin farther away. Around a typical red dwarf, the focal region begins at roughly 250 astronomical units, and red dwarfs account for about 70% of all stars in the Milky Way. That means their focal regions are much closer than the Sun's. But what if, instead of placing a telescope at the focus, we placed a receiver there? Consider a thought experiment. Imagine placing a receiver at the Sun's gravitational focus, while our extraterrestrial neighbors placed another at the gravitational focus of Alpha Centauri. The Sun would amplify the signals they sent to us, while Alpha Centauri would amplify the signals we sent to them. These gravitational lenses could amplify signals by a factor of 1 billion. That means we would need to transmit only an extremely weak signal, yet it could still arrive clearly and accurately without errors or significant loss. Calculations suggest that establishing an error-free data link between the Sun and Alpha Centauri would require a signal power of just 0.0001 watts. The transmitter in your phone uses roughly 2,000 times as much power. And we would not necessarily have to use radio waves. We could use light instead, transmitting data optically and encoding much more information into the signal. Taken together, this means that an extraterrestrial civilization in Alpha Centauri could receive data from us at a rate of 10 megabytes per second, enough to stream high-definition video without buffering, without gravitational lensing. Achieving the same result might require replacing a 1-meter antenna with a telescope 50 kilometers in diameter and increasing the transmitted signal's power to the total electrical output of a small town. The Sun would provide both of those upgrades for free. Imagine a future in which every star system in the Milky Way is connected through gravitationally lensed signals. Information could be transmitted from one end of the galaxy to the other with almost no data loss, traveling at the speed of light, and requiring almost no energy. That would be the galactic internet. More importantly, it might already exist. We may simply never have traveled to the correct location to listen. It is possible that when we finally send a telescope into the Sun's focal region, we will suddenly discover that we are not its only users. Extraterrestrial civilizations may have been communicating through gravitational lenses all along, we have simply never listened from the right place. While researching this subject, I could not help wondering what would happen if we pushed the idea to its limit. What is more massive than a star? A black hole, and not just an ordinary one. What if we used Sagittarius A, the supermassive black hole at the center of the Milky Way? Sagittarius A has a mass roughly 4 million times that of the Sun. Since the power of a gravitational lens scales approximately with mass, its lensing capability would vastly exceed that of the Sun. More importantly, many of the difficulties involved in using the Sun as a gravitational lens arise from the Sun itself. The Sun is a hot, bright, active star. It has a physical surface, a corona, and an overwhelming glare. Supermassive black hole, by contrast, has no surface or corona, and it does not emit blinding starlight. This also means we would no longer have to travel beyond a fixed minimum focal distance. With the Sun, we must travel at least 550 astronomical units because the Sun's physical body blocks light that could otherwise pass closer to its gravitational center. But light passing near a supermassive black hole can skim close to the photon sphere and be bent through enormous angles. Some light can even loop around the black hole itself. Suppose we positioned a telescope 1 light-year from the black hole and aimed it at a planet on the far side of the Milky Way, 100,000 light-years away. In theory, we might be able to resolve individual buildings on its surface. Now imagine looking even farther away. What if we aimed it at a planet in the Andromeda Galaxy 2.5 million light-years from us? We might still be able to see it at a resolution of roughly 1 kilometer. That would be even sharper than an SGLT image of Proxima Centauri b, just 4 light-years away. Planet millions of light-years away could appear more clearly than our nearest planetary neighbor. We could potentially even use the gravitational lens around Sagittarius A to observe a planet in the Virgo cluster, 54 million light-years away. Despite that distance, we might still be able to see its continents, oceans, and even cities. Pause for a moment and consider what that means. The universe has already built a telescope for us at the center of the Milky Way, one that could theoretically give us a clear view of planets millions of light-years away. Unfortunately, even if we could travel at 99.9999% of the speed of light, it would still take 26,000 years to send a telescope to the correct position near Sagittarius A. The engineering challenges involved are far beyond anything we can currently solve. For now. At least, this remains an extraordinarily ambitious thought experiment. The solar gravitational lens is different. It would still be exceptionally difficult, but it is no longer a completely unreachable fantasy. Rests on well-understood physics, concrete mission proposals are being developed, and it could genuinely become achievable within the coming decades. So the question is this: once humanity actually accomplishes this and releases the image, what effect would it have on us if the picture contains signs of extraterrestrial life? How would you feel, perhaps from that day forward? The question of whether anyone else exists in the universe would no longer belong solely to philosophy and imagination. It would become a photograph, a map, and evidence of a real world. We may not be alone in this universe. Discovering what these nearby exoplanets truly look like might make us realize for the first time that those distant points of light are not merely stars in the sky. There may be oceans, storms, continents, and ecosystems around them. Perhaps even another community of living beings looking up at the universe. I hope this happens within our lifetime.